Hi, I'm Kristen Kelton, and I'm an AP Chemistry teacher. Welcome to my active learning presentation on how to teach AP Chemistry, electrochemistry. I'd like to start with the objectives of this presentation. First, I'm going to review the content I'm going to teach. Electrochemistry is a big unit, and I'm only going to focus on a small portion of it. I'm going to show what active learning could look like in AP Chemistry. As a teacher, we're often asked, what does the research say? The methods I have chosen are research-based methods, and I will share that research with you. I would like to share the links with all the resources. Unfortunately, I'm not able to upload links to my description box in YouTube, but the professor will get copies of all of my worksheets and labs when I turn it in Halo. I'm also going to demonstrate how this can be taught in the classroom. As a teacher, I often hear the following three questions. What do we want them to know? How do we know when they get it? What do we do when they don't get it? And sometimes we hear a fourth question. What do we do when they already get it? I like to use a backwards planning model. I look at the standards, I build the assessment, and I work backwards. In this presentation, I'm only going to cover a small portion of an electrochemistry unit. I'm going to focus on batteries. What do they look like? What are the components? How do they work? And pertinent vocabulary. We're going to learn how to calculate electrochemical cell potential, and then we're going to apply the Nernst equation in the lab. Many students struggle with vocabulary, so I've built in quite a few activities that will help with the vocabulary understanding. I'm jumping in to the middle of an electrochemistry unit, so I'm going to assume that we've already covered these prerequisite skills. First of all, I'm going to assume that the students know the rules for finding oxidation numbers. I'm going to assume that they can define and recognize oxidation and reduction, both by looking at equations and by looking at the electrochemical cell potential values. A student should be able to look at an equation and recognize that if the value became positive, it was oxidation, and if the value became negative, it was reduced. I'm also going to assume that we've already covered writing half reactions and the fact that you go from the half reactions to the complete reactions. And one other prerequisite skill, which I will reiterate in this lesson, is the more positive value is the one that gets reduced. Because sometimes students are given two half reactions and they're both reductions. Well, which one was oxidized? Which one needs to be flipped around? So these are the skills that we have already covered. These are the activities and/or resources I'm going to use in this unit. I'm going to use a flipped classroom. I'm going to use two Pogles. One comes from the regular chemistry book, one comes from the AP chemistry book. We're going to create a poster. We're going to do a problem set, which is pretty much just math. We're going to do a really amazing, awesome experiment. And some of the resources that we use is Cam Scanner. Cam Scanner is a free app that you can download to your phone. It allows you to take pictures and then upload it as a PDF. Because my school district uses Canvas, not Halo, Cam Scanner is an excellent way to take pictures of work and upload it to the platform. Other useful sources that I often recommend students go to in all of the units are the Bozeman Science channel on YouTube. Mr. Anderson has many great videos on chemistry, physics, biology, etc. Sometimes we use the PhET simulations on phet.com. Biointeractive, while it does touch mostly on biology, there are some implications where chemistry can come in. I mentioned Pasco because I have the physics equipment, and included in the physics equipment are voltmeters, and I like to use those voltmeters for the experiment. We get really reliable data. It is Bluetoothed to the computer for easy downloading and easy readability. And the last is Flynn Scientific. That's where I get most of my chemicals, and also that's a great place where you can buy the Pogle books that I do reference. As an educator going on her 28th year in education, we're often asked to prove that what we do in the classroom is research-based. Why do we choose certain activities over other activities? And I want to discuss right now differentiated instruction and brain-based learning. Differentiated instruction can take on many different methods. You can differentiate your instruction for an individual, at a class level, but mainly the easiest way to do this when you teach large numbers of kids is to vary the methods you use. Don't just lecture. Lecture, do problem sets, do hands-on activities, do labs. Brain-based learning provides strategies for different age levels that are appropriate for those age levels. And believe it or not, brain-based learning correlates highly with differentiated instruction. In Sousa's book, he points out that if you were to merely lecture and quiz students 24 hours later, they will only recall 5% of the material. If students discuss the material, they will recall 50%. If students do hands-on activities, they'll remember 75%. But when students teach each other, they will remember 90%. So I like to incorporate problem solving from the textbook, and I use the Chemistry, the Essential Science by Brown et al. They also can learn from doing posters, lectures, labs, POGLs. All of these fall into the differentiated instruction piece. I also employ cooperative learning in my classroom, Kagan structures in particular. This helps the students to learn how to help each other, to teach each other, because together we are stronger. It works really well with problem sets, labs, and POGLs. We spend most of our time in cooperative learning groups. I am also now flipping my AP Chemistry classroom. I used to lecture, but I found students, they didn't pay attention. They didn't record notes. They didn't even do follow-along notes. I felt like we were wasting our time. So I'm now flipping my classroom. And that simply means I'm producing videos and posting them online, and I expect them to watch these before class. This allows them to work at their own pace. They can take notes, they can pause, rewind, they can go back to the video later. If a teacher merely lectures in the front of the classroom, that's not possible. This also helps improve 21st century skills, which include collaboration, information, and community technological skills. The research on flipped classrooms shows that a flipped classroom will increase academic performance, student interactions, student attendance, positive attitudes. It allows lower achievers to get more help, because if students really can take something away prior to class from a flipped classroom, they could go ahead and move on with a problem set or a lab during class, allowing the teacher to have extra time to work with those lower achievers. Just because a teacher uses a flipped classroom doesn't mean they don't do anything in class. It actually still requires extensive classroom instruction, but it just looks different. I mentioned I'll be using POGLs and cooperative learning as well. I learned about POGLs 8 years ago when my coworker brought them from Wisconsin. POGL stands for Process-Oriented Guided Inquiry Learning. And we use these in biology, physical science, chemistry. I even use it in physics, because sometimes ones that are published for biology or published for chemistry can be used in other classrooms. POGLs are great. They allow for peer collaboration. They're student-centered. The teacher merely is facilitating their learning, and it allows students to focus on content, processes, and higher-level thinking. I really like the models, the data tables, and the graphs that students have to analyze. I could stand at the front of the room and lecture, but a student is going to understand a relationship a lot more if they find it and discover it on their own. Hand in hand with POGLs is cooperative learning. This is small group learning. Students teach each other. They do have assigned roles, and the positive interactions do lead to increased achievement. Improved peer relationships are also a result. And again, recall what Sousa said. If you lecture, they will only recall 5% 24 hours later. But if they discuss, that improves to 50%. Hands-on learning improves to 75% recall. And if they teach each other, they will remember 90%. It also helps if they're discovering on their own. It really does help the increased retention. When preparing lesson plans, one needs to consider the difficulties students may have. Kempler et al. Did some research and discovered that when teaching electrochemistry, one of the problems is that students need a pretty good background knowledge in heterogeneous reactions, electrostatics, and electrochemical laboratory equipment. Granted, you can teach students how to use the lab equipment, but there needs to be a teaching component to it. Moreover, our lab equipment does not always work, so they need to know how to troubleshoot the lab equipment. I have found that vocabulary stands in the way of learning. If students don't understand the difference between an anode and a cathode, they really struggle to grasp the greater picture. Students have to know how to find oxidation numbers, and again, there's a lot of rules that go into that. They need to be able to identify reduced and oxidized substances. So I take all that into account. When we do the lab, I teach them how to use the lab equipment. All along the way, we are reinforcing pertinent vocabulary like oxidation, reduction, anode, cathode, salt bridge, etc. And before I forget, one of my favorite acronyms is oil rig. Oxidation is loss of electrons and reduction is gain of electrons. I learned that all the way back in college and I still remember it. So using little fun games and analogies and acronyms really can help students to learn the vocabulary. I would love nothing more than for you, my professor, to actually see me in a classroom with students teaching this stuff, but that just isn't possible. So what the rest of the presentation is going to be me pretending I'm talking to my students, that they're watching one of my flipped videos, and every day they have to watch a little piece of the video in preparation for the next day so that they know what we're going to be doing, why we're doing what we're doing, and what we were supposed to get out of it. All of the labs and assignments are in my Word document that I turned into Halo. Hey class, let's take a look at where we've been and where we're going in part 2 of electrochemistry. Where have we been? Well, so far you've learned to find oxidation numbers, determine the change in oxidation, identify who's oxidized and who's reduced, both by looking at the equation and by looking at electrochemical cell potential values. You've learned to write half reactions, and you've learned to write complex, complete reactions in acidic solutions and basic solutions. Next, in our part 2 of electrochemistry, we're going to dive more into the voltaic cells, the batteries. What are they composed of? How do they work? What's the vocabulary surrounding batteries? We're going to look at calculating electrochemical cell potential. I promise you, it's easy. And then we're going to look at the Nernst equation, which will allow us to determine electrochemical cell potential when we do not have standard conditions. In part 2 of electrochemistry, we're going to do, again, a video lecture, that flipped classroom we've been using all year. We're going to do 2 POGLs, one on batteries, and it's pretty easy. It's just from the regular high school chemistry POGL book. And then electrochemical cell potential. We're also going to do a battery poster, really solidify not only the flow of electrons and the flow of ions, but really get that vocabulary down. Of course, we're going to do a problem set from our textbook. And last, we're going to wrap it all up with the electrochemical cell potential lab, which I know you're going to love. Before we dive into this part of electrochemistry, I want you to go ahead and watch the lecture for this section. See Canvas, the link is there, or go straight to my YouTube channel and look for Electrochemistry Part 2. I do want you to pay attention to a few things in the lecture. Again, you may want to pause and take notes. What are the parts of a battery? How is it we would build one in the lab? Just exactly how does this voltaic cell function? Why do the electrons flow? How do you calculate standard cell potential? How can you relate standard cell potential to Gibbs free energy and equilibrium? And lastly, go ahead and write down and take a look at the Nernst equation. This is the equation that will let us calculate the standard cell potential when we are not at standard conditions. Now that you've watched my video on electrochemistry part 2, in class we're going to do the battery POGL. You're going to access it in Canvas. It's a Google Doc. We're going to work in our cooperative groups. Do not leave anybody behind. Make sure everybody understands and gets the most they can out of this. You will have the first 25 minutes of class to work on it. Then we're going to spend the other 25 minutes going over the POGL. But instead of me giving you the answers, each group will share answers. Not only will you give the answer, but you need to be able to tell us where you found the answer or how or why that is the answer. Now, why are we taking class time to do a POGL? Because it's important. Here are the goals or the things I want you focusing on. I want you to be able to explain the changes in ion concentration. There are ions moving in several different locations. Where, how, why? I want you to be able to determine how to know which metal is oxidized and which is reduced just by looking at a model. You're going to determine the directional flow of electrons. You're going to be able to label anode and cathode. You're also going to be able to explain how a solution stays neutral. Good evening, class. So today in class, we did the battery POGL in our cooperative groups. We went over the answers and explained how, where, why those were the answers. But let's just recap. Or as my old college professor said, what's the take-home message? Here are the key things you should have gotten out of today's POGL. Electrons flow from the anode to the cathode. They go from negative to positive. The salt bridge is vitally important. Without it, the solutions do not remain neutral. As the cathode loses positive ions out of the solution, as those go up to the metal, positive ions from the salt bridge will replace them and keep that solution neutral. Likewise, in the anode, the electrons are leaving the solution, and that starts to make that solution kind of positive. So the negative ions will flow toward the anode. And remember, cathode goes with reduction, anode goes with oxidation. Some people say an ox, red cat. I'm a little bit more of an English person. I like to think of anode and oxidation, both are vowels. Cathode and reduction are consonants. That's how I remember it. And then, of course, anode, anti is negative, so the negative flows toward the negative. And of course, we all remember that cathode are cats, and cats are positive. So that's why the positive ions flow toward the cathode. So that you can make the most of your class time, let's preview the battery poster assignment tonight. You can find the link in Canvas. It tells you everything you need. It tells you why we're doing what we're doing, and of course, a scoring guide. The point of this is to draw by hand a functioning voltaic cell or battery. I'm looking for a metal in its solution, another metal in its solution, and I'm looking for actual metals, so you'll need to do a little research. I want you to label all of the pertinent parts, show the flow of electrons, show the flow of the ions, so you'll need to be thinking about ion concentration and what's happening in the voltaic cell. There is also one small piece where you have to explain something. The point of this is that you can solidify in your mind the vocabulary associated with batteries and the flow of direction, the flow of the electrons and the ions. Good evening, class. Let's preview tomorrow's in-class time. You're going to be looking at the electrochemical cell voltage POGL. Again, it's a Google Doc and Canvas. We will work in our cooperative groups. I will give you 25 minutes of class time to work and 25 minutes to go over the POGL. Again, I'm going to be asking for answers as well as how did you come to those answers? Did you find it in the data table? Did you find it in the model? Did you draw upon other information? Where did you get your answer? And then tomorrow night, I will recap what you should have taken away from this POGL. Good evening, class. Let's do a quick recap of the electrochemical cell voltage POGL and what you should have gotten out of it. You should have noticed that there is a relationship between concentration, equilibrium, and electrochemical cell potential. I mean, who knew Le Chatelier was coming back, right? As the concentrations change, equilibrium shifts depending on what concentrations change. You might make the reaction go forward, it might go in reverse. And when that equilibrium shifts, it changes the electrochemical cell voltage. You should have recognized that positive E values are spontaneous and those that are negative are not. More importantly, this is going to bridge us into the problem set and into the lab that we're going to do. If the reactant concentration decreases, the equilibrium is going to shift in reverse back to the left, and your E value will decrease. As the product concentration decreases, equilibrium will shift forward and the E will increase. When the reaction goes forward, E increases, but when the reaction goes in reverse, it decreases. So if you want to increase E, you need to make the reaction go forward in whatever way that takes. To decrease E, you want to shift the reaction to the left. Now, what they started hinting at in this POGL that will then become important when we get into the lab and in the problem set is that when Q increases, E decreases, and vice versa. This is going to play out in the Nernst equation, and when you look at the math of it, it will make sense. Are you still hanging in there with me, class? We don't have a whole lot more to cover in this unit. Tomorrow, we're going to tackle some problems. And again, the worksheet is in Canvas. I do want you to do all your work on paper, upload it using Cam Scanner to Canvas. Must show all your work to get credit. Showing your work is way more important to me than an answer. And there are other similar problems that can be found in your textbook, Brown et al. 2015 in Chapter 20. It's always great to do more practice than I give you. So what is the point of this problem set? What are your goals? I want you to be able to thoroughly explain the relationship between E, delta G, and K. How do they all interrelate, and how do we calculate all of them? You're going to examine an equation to determine which is oxidized and which is reduced. We're going to review writing half reactions. You're going to identify anodes and cathodes and their signs, positive, negative, that kind of a thing. Determine the directional flow for ions and electrons based on a situation. Determine E, G, and K values for reactions. You're going to sketch and label a voltaic cell, which should be pretty easy since you did the battery poster. And you're also going to use the Nernst equation to predict the electromotive force values at non-standard conditions. And that's a really key problem to understand as we're going to use that in our lab. Good evening, class. And the moment we've all been waiting for. That's right. Tomorrow and the next day, we are going to be working our way through the electrochemical cell potential lab. Now, this is a lab that I based on Sally Ann Vonderbrink's lab. I made a few changes, mainly to the more complicated math questions. I've given you a few extra hints and a few extra steps to help you with the complicated math. So, as my husband always says, when all else fails, read the directions. You are going to work your way through this lab with your group. The first thing you're going to do is you're going to create your own appendix. Now, the appendix in your book has hydrogen as the standard. You'll notice that it has an E value of 0. You are going to make your own appendix with zinc as the standard. Then once you have those values, you are going to do a little inquiry. You're going to choose 2 different metals, build a voltaic cell, and based on your reduction potential standard, you are going to then determine or predict what the voltage would be. You're also going to write the half reactions, write the complete reaction, and these are relatively easy to do in your head, but feel free to jot them down on a piece of scratch paper. Just don't forget, before you add the half reactions, you got to make sure the electrons are conserved and cancel out. So once we've done that, we're going to get into the slightly more complicated part of the lab. In part 3, you're going to change the concentration of the reactant. You're going to use the Nernst equation to predict what the E value should be. Then you're actually going to create the voltaic cell and measure the E value. It's pretty cool. We're usually pretty close between predicted value and experimental value. In the fourth part, you're going to build a voltaic cell and get the E value, and then use the Nernst equation to ultimately calculate KSP, the solubility product constant. And then in the fifth part, you're going to use the Nernst equation and the E value to calculate the formation constant. And then later on in one of the questions, I'm going to ask you to compare the KSP value and the KF value to what you would normally find in a resource guide. Just how close were you? So what I really like about this lab is that it takes everything we've done, pulls it all together, and just helps you to really reflect upon all of the vocabulary and all of the math we've done thus far. Whew, we got that done in about 2 class periods, 50-minute class periods that is. Let's go ahead and take a look at the take-home messages from the lab. You made your own appendix, so to speak, with zinc as the standard. You used the data from your appendix to predict E values for different chemical combinations. You used the Nernst equation to predict potential and then compared it to the experimental data, and we were pretty dang close. You decreased the concentration of a reactant, and you saw that that decreased the voltage. You should have noticed when you did the math why that happened. When the reaction shifts to the left, Q increases. And when you look at the Nernst equation, that ultimately brings the value of E down. And that is a key concept. You need to know that for the test. We also use the Nernst equation to calculate concentration, which then led us to calculate KSP and KF. Give yourself a round of applause. You made it to the end of the unit. In this last half of electrochemistry, you looked at batteries, what they're composed of, how they work, and all the vocabulary pertaining to voltaic cells. You can now calculate electrochemical cell potential both for standard and, thanks to the Nernst equation, non-standard conditions. The only thing you have left is to prepare for your unit exam. Get onto Canvas, look at your practice test, and take that practice test as many times as you need to in order to get the best grade and to prepare yourself for the unit exam. Be really proud of yourselves. You did it. All right, I'm no longer in my AP Chemistry teacher mode. I'm back to the professional educator. And I thought, since I'm publishing this on my public YouTube channel, maybe there's a teacher out there who watches this and wanted to know what those links were. So here are the links to the websites that I mentioned earlier. The Biointeractive, the CAM Scanner, you can also find it in the App Store, Bozeman Science, Flynn Scientific, Pasco, again, great equipment at Pasco, great stuff that Bluetooths to your computer, the PhET simulations, and of course the Von der Brink Lab Manual. I mentioned earlier that I made a flipped video for my class, and in case an educator was interested in it, I wanted to go ahead and include that. The Electrochemistry Part 2 is the flipped video I expect my kids to watch, and I do plan to use it in my AP Chemistry class. And in case any educator would like to check out the other silly videos I've created for AP Chemistry, that is my YouTube channel. Thank you. One last thing. There are some great resources out there to help educators. Everything from flipped classrooms to cooperative learning to brain-based learning and differentiated learning. Hopefully, here are just a few that can help any educator further their research abilities in becoming a much better teacher.